Video course on statistics. From basics to advanced subjects. Dr. Yahya El-Maghazi, Professor Emeritus at Auburn University, Alabama, USA. Former Dean of Science, Technology, Math, Engineering at Ocean County College, New Jersey. A visiting professor at a number of universities including Rowan University, Keene University, and Montclair University, New Jersey, USA. Inferential Statistics. Part 5. Hypothesis Testing.
This session is about a real important subject, which is what I consider the second or the other side of the coin of inferential statistics, and that is the hypothesis testing. Hypothesis testing is about a claim made by someone that has to be tested and has to be verified. It's really a different format for estimating population parameters from sample statistics. So we're still about making claims about the whole population. We're still about estimating population parameters from sample statistics. It's a different form from the classic estimation that we did in previous sessions, where we are not only about establishing a confidence interval, but we are also about testing specific claims, and via a number of systematic steps, as we will discuss very shortly, and see whether we will accept or we will reject a claim. As you go through this chapter, you will find that you have already learned most of the contents of this chapter. So the focus here would be about the application and how we use test of hypothesis in real life or real world applications. Let us start with our slides now and see where we go. The first question we have to ask is, what is hypothesis testing? Hypothesis testing is a contention based on some pre-assumptions or preliminary observations of what appear to be facts which may or may not be true. That is the whole issue of hypothesis testing. A contention based on some past observations or some general knowledge of what appear to be facts which may or may not be true. And it is our job to actually decide or determine whether this contention is true or false. The test of hypothesis compares the contention with the collected facts, and the collected facts in this case would be data via a sample selected from the population. If these facts can be shown to agree with the contention is retained. That is, the hypothesis is accepted. If the contention and the facts, on the other hand, do not agree, the contention is discarded and we have to reject the hypothesis in this case. Let's take an example for illustration, and there are really many examples. Suppose a company has received a claim from a supplier that the metal rods supplied have mean diameter of, say, 5 millimeters. The company can test this claim by formatting a simple hypothesis. After all, the issue is about one value, which is the diameter of a metal rod. So in this case, the format of the hypothesis test will look like this here, where we have H0 and H1. H0 is what we call the null hypothesis, and the H1 is what we call the alternative hypothesis. The null hypothesis deals directly with the claimed value. So the 5 millimeter here will be the mu zero. The alternative, of course, will be the opposite or the complementary hypothesis to the first one, meaning if this is equal, this will not be equal. Of course, there are other alternative hypothesis format, as we will see very shortly. So for this example, the null hypothesis will be that mu equal 5. The alternative hypothesis may be mu not equal 5. It may also be mu greater than 5 or mu less than 5. So we have basically three alternative hypotheses, but for this example, since we're dealing with diameter, and diameter is normally nominal, the best type variable, then it's reasonable to say that the alternative hypothesis will be mu not equal 5. So H0 is called the null hypothesis, a claim or a statement about a population parameter that is assumed to be true until it is declared false. In this case, the claim is that the population's mean value of rod diameter is 5 millimeter. H1 is called the alternative hypothesis, and it implies that the average diameter of the rod population is not equal to 5. So you can see the basic format of a null of hypothesis testing. As I mentioned earlier, there are different forms of hypothesis testing. Here is one form here where we are talking about null hypothesis, mu equal the claimed value mu 0, and the alternative in this case will be mu not equal mu 0. The second case, mu less than or equal mu 0, and the alternative will be mu greater than mu 0. Note that the null hypothesis and the alternative hypothesis are mutually exclusive. So if we accept that mu is less than or equal mu 0, then we definitely have to reject that mu is greater than mu 0. Same thing here, we have a different form which said H0 mu greater than or equal mu 0. The alternative in this case will be mu less than mu 0. It's very important that we understand the different forms of hypothesis testing, because it's our job to actually format or establish the hypothesis depending on the application in hand. Most stat books and most statisticians would like to think of hypothesis testing as a series of systematic steps that need to be followed. And this is very much true, although there will be some judgmental issues between the different steps. The first step is to identify and define the characteristic under consideration and state the null and alternative hypothesis about the value of the characteristics in the population. It's very important that we establish our hypothesis, the null and the alternative, before we can move on to the next step. So now that we have the hypothesis format, we'll move on to the next step, which is to take a sample from the population, test it, collect data, and determine descriptive statistics of sample data. This should look very familiar because that's basically what we did in the classic estimation or inferential statistics, where we took a sample from a population and we determine the statistics of the sample so that we can estimate population parameters. So this step will be repeated here. In most application, the common descriptive statistics are the average of the sample, the standard deviation of the sample, and of course the sample size. The next step is to select the level of significance. We did that in estimation, and we will talk about this very, very shortly. And the fourth step is to identify the appropriate test statistics. We will also discuss that shortly. And finally, the final step is to follow some decision rules to determine whether we reject the null hypothesis or accept it. Keep in mind that rejection or acceptance is all about the null hypothesis, the H0. Let's take these steps one by one and discuss it a little bit further. The first step is to identify and define the characteristics under consideration and state the null and the alternative hypothesis about the value of the characteristic in the population. In this regard, we need to divide our variables into three main types. First one is nominal the best. Most dimensional characteristics are nominal the best. These are the variables that we don't want it to be too large or too small. We want it to be exact. When we talk about the metal rod diameter, we want the diameter to be exact, 5 millimeter. Similarly, if we're talking about ceramic tile area, we want it to be exact. We are not interested in having larger tile or smaller tile, the exact value. And there are many, many examples in practice that follow nominal the best, mostly dimensional characteristics. Anytime you talk about thickness, area, diameter, time, if it's exact time, for example, a test time should be exact. In many situations, we have to deal with nominal, the best variables, and the best format of hypothesis for that is equal versus not equal. Other situations may involve the so-called larger the better variables. People income, students from their own point of view would like to have the highest grades possible. So these are all larger the better variables. And in this case, the best way to format a hypothesis will be to follow this format here, mu greater than or equal some value, and the alternative to that would be mu less than some value. For example, if we're talking about income, mu greater than or equal $50,000, while the alternative will be mu less than $50,000. The third category is the smaller the better variables. That's percent defects in product, for example, or returns, or anything that has to do with defects or in general bad news, failures, rejections, returns. All of these follow the so-called smaller the better variables, where the best way to format the hypothesis will be a null hypothesis of mu less than or equal mu 0 and alternative mu greater than mu 0. If the variable, for example, is percent rejects, then less than or equal 5% would be the null hypothesis. Say that the claimed value is 5%, and the alternative will be mu greater than 5%. The point that we have to make here, and let me just address that directly, is that it's very important that we use a great deal of judgment in establishing the format of the hypothesis test. If you are a student dealing with a problem of hypothesis test, unless you specify what hypothesis test format you used, then anything comes after that will be meaningless. You have to use some judgment. In many cases, we actually tell you what to do, but it's even better in line of critical thinking that you develop your own hypothesis format. What we just discussed with you are just examples. When you see a variable that's nominal the best, then more than likely you want to use the equal versus the not equal. When you see a variable that's larger the better, then maybe you want to look at greater than or equal versus less than. When you see a variable that's smaller the better, then you may want to use the less than or equal versus the greater than. So judgment is a key aspect in formatting the hypothesis testing. Let's go back to the slides and continue with the steps. Step 2. Step 2 is, we should be familiar with this step. We take a representative sample from the population. After all, keep in mind that all these hypothesis testing is about the population, not the sample. But in order to get to the population, we have to take a representative sample from the population, test it, collect the data, and determine descriptive statistics. And as I mentioned earlier, the key descriptive statistics in most of the applications we will have here will be the average of the sample, the standard deviation of the sample given the sample size. And we discussed the issue of minimum sample size in a previous session, which I believe should be revisited at this stage to know what is the optimum sample size used to perform inferential statistics or hypothesis testing, as indeed the sample size can be a factor in your decision. The third step is to select the level of significance. When we say the level of significance, in the classic estimation, we have used confidence levels such as 95% or 99% or 98%. Here we have to pause a little bit and discuss very, very important issue. That is the so-called type 1 error and type 2 error. Type 1 error is if the null hypothesis is rejected when it is true. Then a type 1 error has occurred. Can this happen? Yes, due to one reason or another that we will see by examples very shortly. When you reject a hypothesis while it is true, it simply means you have something that is indeed true, but you're rejecting it, which means you have to do something about it. For this reason, we call it over-controlled thinking, or incorrectly modifying a process while the process is actually doing fine. The way we describe this statistically is we say alpha, or the type 1 error, is the probability of type 1 error, or the probability of rejecting the null hypothesis while it's true. The type 2 error is if the null hypothesis H0 is not rejected when it's false, then a type 2 error has occurred. This may lead to an opposite action to that of type 1 error or under control. The probability of type 2 error is the probability of failing to reject a null hypothesis while it is false. The fourth step is to identify the appropriate test statistics. We will discuss that in the next session. Mainly, there are two statistics that we will deal with. The Z statistics for large samples and population variance known, and the T statistics for small samples or population variances unknown. We will see that by example in the next session. And the final step will be to follow appropriate decision rules to reject or accept the null hypothesis. We will discuss all these steps using examples to illustrate how we can follow these steps systematically. Meanwhile, how we can use our own judgment in making sure that as we move from one step to the other, we are doing the right thing. In the previous session, we discussed the 5 basic steps to perform hypothesis test. We said we have to identify the variable, and identifying the variable will lead us to identifying or establishing the format of hypothesis testing. Then we go to collect samples from the population, determine the descriptive statistics of the samples, mainly the mean, the standard deviation, given the sample size. Third, we establish the significance of our decision, and in this regard, we discussed type 1 and type 2 error and how we avoid these two types of errors if we have the luxury to select a large sample. The next step was to select the appropriate statistics for the test, and then finally to make the decision or establish criteria to reject or accept the null hypothesis. We will start this session with the 5th step because we need to dwell on that a little bit, as this will be the most important step in these 5 steps. That doesn't take away any of the value of the other steps, but this one is where we have to make a decision and we have to understand how we make that decision. Let's go to the slides and see, starting with step 5 in hypothesis testing. We said we follow appropriate decision rules to reject or accept the null hypothesis. Now, the final result will always be to either reject or do not reject. And I emphasize that what we are rejecting here is the null hypothesis. And what we don't reject is also the null hypothesis. Now, there are 2 approaches to determine whether we reject the null hypothesis or not. The first one is what we call the critical region approach, and we will see that by example shortly. In this approach is we compare the test statistics, Z or T, and these 2 statistics are now should be familiar. So we're going to compute or calculate 2 statistics here, depending on the case, either Z or T. And we will compare that with the so-called critical Z or T. The critical Z or T are the ones that we obtained from the tables in earlier session. And we will see how the two compares, and we will define a rejection area by which, based on that comparison, we can reject or do not reject. The other approach is what we call it the p-value approach, which is an area value. We will have to determine how the area corresponding to the Z or the T statistics compared to the type 1 error area. That's the 5% or the 1% area, as we will see shortly by example. This table here is very important, and you will see it in many books. You will also see it in your textbook. And this table actually summarizes for us the 5 steps in a very nice way. We will have cases where we will deal with a larger sample where the population variance may be known, and in this case we may choose one of the 3 format of testing: two-sided if it's nominal, the best variable, or one-sided, and if it is larger the better or smaller the better. And after we select, say, the two-sided, we go into formatting the hypothesis test, mu equal versus mu not equal. And then the next step after that, we determine the statistics or the test statistics. This is, for example, for the large sample or variance known. And as you can see here, the Z statistics is calculated by the average of the sample X bar minus the claimed value. Keep in mind that mu 0 here is not the actual mean of the population. It is the claimed value of the mean of the population, the mu 0, from the format of hypothesis testing. So this is the Z statistic that we use. Now, the next one here is the critical Z, which we are familiar with. This alpha over 2 can be 5% or can be 1%, depending on the type 1 error that we are willing to take, the risk we are willing to take in making the decision, in other words. So we will compare the Z0 with the Z alpha over 2, and we will see whether the Z0 is actually in the rejection region or not, as we will see by example shortly. We will repeat these steps for every case here in the table. If we are dealing with one-sided left, this will be the format of the null. This will be the format of the alternative. The Z statistics will be the same. The critical area will be different. As you notice here, we have Z alpha because we are going to put all the risk in one side. That's a one-sided test. And then we're going to go and see how we Z0 compared to Z alpha. Same thing for the right-sided. Here is the null, here is the alternative, same Z statistic, same Z alpha, and we will seek a comparison between the two. It's very important that we understand how we go from formatting the hypothesis to rejecting a hypothesis. For example, if we are taking the first case, where mu equal mu 0 is the null hypothesis, mu not equal mu 0 is the alternative. In this case, we have to sketch the normal distribution and think of the critical value Z alpha over 2, and we say alpha over 2 here because as we discussed in the confidence interval in early sessions, if we decide our confidence to be in the middle, which is right here, then we divide our risk into two sides, alpha over 2 and alpha over 2, meaning the middle area here will be 1 minus alpha, and as you know, the area under the curve is 1. So this would be the 95% confidence. This will be 2.5%, 2.5% in this side, meaning the outside area will be 5%. And that will follow this hypothesis format. Now notice the Z0, which will be calculated independently because it's a function of the average of the sample, the claimed value, the standard deviation, and the sample size, may either go on the rejection side or the not reject side. Keep in mind that as soon as we establish this sketch here, we decide that the area in the middle, the 1 minus alpha, which is our confidence area, is the do not reject area, while the areas outside are the reject area. So if the Z0 came out to be outside, we will have to reject the hypothesis, the null hypothesis. If the Z0 came to be in the do not reject area, we will have to not reject the null hypothesis. Here is the case for the one-sided, where we are putting all the risk in one side. In this case, you can see the alpha is entirely in one side of the curve, meaning the 95 or the 99% confidence will represent this entire area to the right here. That's the 1 minus alpha. And again, if the Z statistics fall in the do not reject area, we will not reject. If it falls in the reject area, we will reject. Same thing for the left side. For the right side, I mean, here is the entire risk on the right side. This is the do not reject area, or the 1 minus alpha. And depending on where the Z0 will fall, we will make the decision about rejection or acceptance of the null hypothesis. The p-value or the probability approach is really quite similar to the critical region approach. And as you can see here, we're following the same procedure. Here is the null hypothesis. Here is the alternative hypothesis for two-sided. The Z statistic is the same. But this time, we're going to determine the area or the probability corresponding to the Z0. And we will see whether this area is smaller or larger than the critical area. And what's the critical area? The critical area is our type 1 error, the 5% or the 1%, as we will see by example very shortly. Same thing for each case, as you can see here. So really using the tables that we just addressed or discussed will be very useful in dealing with the problems of rejection or acceptance of null hypothesis. Again, if we are dealing with the p-value approach, then what we are really after is an area corresponding to the Z statistic or the T statistics, as we'll discuss later on. It's that red area here compared to the critical area, which is the alpha over 2 in this case. If it is smaller than the critical area, then it's actually in the rejection area, as you can see, meaning we have to reject the null hypothesis. If it is larger, then we'll have to accept. Here is the same thing. Here is the area that we will have to determine based on the Z statistics that we will calculate. As we can see here, there is some effort in determining whether we should reject or fail to reject the null hypothesis. There are two approaches. One is the critical region approach, and the other is the area approach. The two approaches really go hand in hand because they are about the same thing. We are looking at a sketch of the normal distribution. We define a rejection areas, which are the areas determined by the type 1 error. We may divide this into two sides in case of the nominal the best or equal or not equal, or we may allocate the entire risk in one side of the population. But in either case, we have a rejection region and we have a do not reject region. And the whole issue here is about comparing the Z statistic determined from the sample statistics as well as the claimed value with the critical value. The area approach is comparing the area corresponding to the statistic, or the Z statistic, and the area corresponding to type 1 error. Perhaps the example that we will discuss in the next few sessions will help a great deal understanding the 5 steps of hypothesis testing. We'll see you in the next session. In the previous 2 sessions, we went over the basic steps of hypothesis testing. And I'm sure some of you are still puzzled by so many of what we discussed, because all what we discussed are many rules and methods that have not materialized into examples. In this session, in the next one, we will give you practical examples that I'm sure after you listen to it, you will understand the basic steps of hypothesis testing and how we go about implementing these steps. Let us start first with the first case, and we're going to deal with two cases which is in parallel with what we discussed in the inferential statistics or estimation. The first case will be large sample taken from a population or the variance of the population is known. And in this case, we need to keep in mind the Z statistic. The second case, which will be discussed in the next session, will be a small sample and the variance population is unknown. And in this case, we will use the T statistic. You can see how parallel the hypothesis testing is to the estimation. So let's go to the slides and see the first case and see how we implement the 5 steps of hypothesis testing. You will find me repeating myself if you have followed the estimation sessions in terms of the conditions and the scenarios that we have to deal with in the test of hypothesis, because they are identical to those that we mentioned early with the estimation process. Typically, there are 2 scenarios that one will face whether you are doing estimation or establishing a confidence interval or you are doing a hypothesis test. The first scenario is the population standard deviation is known, and the second scenario is the population standard deviation is unknown. I also mentioned that if the population standard deviation is known, then we have to look at the possible situations under this condition, which is when the sample size is large, equal or greater than 30, and the sample size is small, less than 30, but we are willing to assume that the population is normal, and in both cases we use the normal distribution or the Z statistic. If the sample size is less than 30 and the population is not normal, then we have a problem, and in this case we have to use a non-parametric statistics, which is not the subject of this course. Let's start with the case of hypothesis tests for a population mean mu when the standard deviation sigma of the population is known. In the bottom table here, you will see some values of Z at different values of alpha, which will assist you instead of having to go to the standard normal table every time you do a hypothesis test. These values are at alpha equal 0.1 or 10% type 1 error, and 5% type 1 error, and 1% type 1 error. And that is for both the two-sided, as you can see here, and the one-sided. Here is an example. Determine the Z statistic and the critical Z value, and make appropriate decision for the hypothesis test for the following case. We have here the average of the sample x bar equal 80, sigma or the standard deviation of the population equal 5, sample size is 40, and we have a claimed value of 82, and we are to do or perform the hypothesis test at a type 1 error equal 0.05 or a risk of 5%. Now, the standard deviation population is known, so we're going to use the Z statistic. Now, this is the general format of the hypothesis test that we will do. So that is basically step 1, establishing the hypothesis test. So in this case, the claimed value is 82, and if the claimed value is 82, then this is the value of the population mean corresponding to the null hypothesis, H0 equal or mu equal 82, while the alternative hypothesis will be mu not equal 82. So here we established the hypothesis test format. This is essential before you take any further steps in performing hypothesis testing. If you recall, step 2 was about the sample. Taking a sample from a population and finding the statistics of this sample. Here we are giving you the statistics, the x bar equal 80, and we have a sample size of 40. We need these two values in order to complete our test of hypothesis. Step 3, determine type 1 error. In practice, you normally have to decide yourself on type 1 error, but in this problem we are giving you type 1 error 0.05, which is the value corresponding to 95% confidence, and as a result the Z value, if you recall, was 1.96. The next step, we have to calculate the Z statistic or the Z0, and as I mentioned before, it is calculated from x bar minus the claimed value divided by the standard error. Now x bar is 80, the claimed value is 82, and the standard error is determined by the standard deviation of the population, which is 5, divided by the square root of the sample size, which is 40, and that gives us a Z statistic of minus 2.5298. Now, in order to decide whether we should reject or fail to reject the hypothesis test, we have to compare the Z statistic with the critical Z value. So these two values will have to be compared. These are the two values that we are interested in our final conclusion of whether we reject or not reject the hypothesis test or the null hypothesis. Again, here are the steps, and we reach the point that we need to make a decision, the decision rule. And based on what I discussed a few minutes ago, we have to look or sketch the normal distribution, as you can see here, and we specify the rejection region and the no rejection region, and you can see in a two-sided test, this is the typical view of the normal distribution, where the critical points are at the Z of alpha over 2, because we are dividing our type 1 error into two halves, alpha over 2 here and the alpha over 2 here, meaning we have a confidence of 1 minus alpha in the middle. In our case, we have a 95% confidence, so alpha over 2 is 0.025 here, 0.025 here, and as you recall, at 0.025, the critical Z value was 1.96 minus to 1.96 plus. Now, where is the Z0 stands in this sketch? Now the Z0 is minus 2.52. So minus 2.52 obviously will be right here or in the rejection region. And what does that mean simply? It simply means we have to reject the null hypothesis. We have to reject that mu is equal 82. And there is a good likelihood that mu is not going to be an 82. Another method used to assist in making the decision of whether to reject the null hypothesis or fail to reject is the so-called the p-value approach. And here we have basically four tasks. Number one, as we did before, we will determine the Z statistic. Number two, we will calculate the p-value for the test statistic, meaning we will have to go to the standard normal table and find the area corresponding to the calculated Z value. Number three, we have type 1 error, or we have to decide on type 1 error. And number four, we have to compare between the p-value corresponding to type 1 error with the p-value corresponding to the test statistic. And if the p-value corresponding to the test statistic is smaller than the p-value corresponding to type 1 error, then we will reject the null hypothesis in this case, as you will see shortly by example. Here we are. We have the same example we just addressed, and recall that we rejected this null hypothesis using the critical z-value. So let us try to see how we handle the same test using the p-value. Here we have the sample statistics, we have the type 1 error, we calculated the Z statistics. I'm repeating everything that I did in the previous case. And now we reached the Z statistic, or the value of minus 2.5298. We will then have to see what area under the normal curve or under the standard normal curve correspond to this Z statistic. So we have to go to the standard normal table and define the area corresponding to minus 2.53, which is this area here, and this came out to be 0.0057. Now remember that this area is the area to the left from minus infinity to the z point. So in other words, this area in our case will be somewhere here. So recall that the critical area of type 1 error was 5% type 1 error divided into two parts, each of 0.025. So 5% type 1 error means that we have to really multiply this area here by 2, which will give us 0.114. And what does that mean? It means we have an area corresponding to the Z statistic that is less than the area corresponding to type 1 error. And that is a reason to reject the null hypothesis. In fact, if we sketch this area roughly, we're going to find it looking like this dark area here. And as you can see, the area or the p-value corresponding to the Z statistic is much less than the critical area at 0.025, and as a result we have to reject the null hypothesis. You can see that either using the critical Z value or using the area corresponding to the Z statistic, both methods will lead us to the same decision. Let's take another example, and this example we need to pay attention to it because we're going to review some of the previous concepts or aspects that we discussed in earlier session, so we can wrap up the aspect or the concept of inferential statistics. A publishing company has just published a new college textbook. Before the company decides the price at which to sell this textbook, it wants to know the average price of all such textbooks in the market, so that you can offer a reasonable price comparable with the prices of similar books. Now, there was a claim that was made by other publishers that the mean price of this type of textbooks should be $150. So that is our claim value. That is the mu 0. Now, the research department at this company took a sample of 25, that's a sample size, of comparable textbooks and collected information on their prices. This information produces a mean price of $145. So that is X bar. So now we have N and we have X bar. Now it is known that the standard deviation of the prices of all such textbooks is $35. So now we know the population standard deviation. And we also know that the population of such prices is a normal distribution. And the question here is we need to verify the claim at 10% type 1 error. What claim? The claim is the comparable price or the mean price of this type of textbooks should be $150. So we have all the information now to perform the hypothesis test. We have X bar, we have the standard deviation of population, we have the sample size, and we have the claimed value, and we also have the type 1 error at 10%, or if you recall, that corresponds to a 90% confidence in the estimation process. Now step 1, we establish our test of hypothesis format, mu equal 150, that's the claimed value, versus mu not equal 150. So the null hypothesis is mu equal 150, the alternative hypothesis mu not equal 150. Step 2, we make sure that we have the sample statistic that we need, the X bar. We also have the sample size. Step 3, we make sure that we have type 1 error, or the value of type 1 error. In this case it's 0.10, and if you recall, at 0.10 or a confidence level of 90%, we have a z-value of 1.64. Now step 4, we calculate the Z statistic, and it's simply calculated, as I mentioned before, using this formula, X bar minus the claimed value divided by the standard error. X bar is 145, the claimed value is 150, the standard deviation is 35, and the sample size is 25, and that gives us a Z statistic of minus 0.714. And once again, once we calculate the Z statistic, our next step is to establish the decision. Are we going to reject the null hypothesis, or we will fail to reject it? And the key here is to compare the critical Z value with the calculated Z value, the Z statistic. So our purpose here is to look at these two values very carefully and compare between the two. Now, again, to help us comparing the two values and make the decision, we have to sketch the problem. So here we're sketching the normal distribution. We have the critical values at minus 1.64 to plus 1.64, and all what we have to do now is to find whether the Z0 or the calculated Z statistic is within the don't reject area or in the rejection area. And as you can see here, at minus 0.714, the Z0 will come here, which means we cannot reject the null hypothesis because the Z0 falls within the do not reject area. So the decision is do not reject the null hypothesis, or based on the sample statistic and the information we have, we simply cannot reject the null hypothesis, and we're going to have to assume that 150 sounds like a reasonable price for the textbook that this publishing company is selling. Again, if we're going to use the p-value, remember our Z statistic was minus 0.714, so we can actually look at the area corresponding to this Z statistic, which has 0.71. What we have here, remember, it's 0.714, so we're going to go at 0.71, which is 0.2389, and since this is a two-sided test, we multiply this by 2, that will give us 0.4778, or much greater than the 0.1, which is the type 1 error, meaning that if this is the critical area here, then the area corresponding to our Z statistics will be far outside or greater than the critical area, and as a result we cannot reject the null hypothesis because we are overlapping with the do not reject area, as you can see in this case. We're now going to move to how to verify whether what we did is actually correct or we have a problem. Now recall that the average was $145 based on the sample of the textbooks that we analyzed. The standard deviation of the population was 35, the sample size was 25, and the claimed value was 150, and the type 1 error was 10%. Now, if you go back to previous sessions of how we estimated the mean of the population, this was the formula to estimate the mean of the population. Mu, or the mean of the population, was x bar plus or minus z times sigma over the square root of n. And if you also recall, this was the standard error, and this entire value, or the product of z times the standard error, was the margin of error. Now, if we substitute the values here, we will have mu equal 145, the point estimate, plus or minus z value, which, as you recall, it was 1.64 times sigma 35 divided by the square root of sample size 25, and now we have the standard error being equal 7 times the z value. That will give us the margin of error of 11.5. You need to also recall that this is the absolute margin of error. The percent margin of error is determined by dividing this absolute value by the point estimate times 100, as you can see here. 100 times 11.5 divided by 145, and that gives us 7.93%. Now, what does this mean? What does this estimation mean to us? Well, it simply means that at 90% confidence, we have a estimation of the population mean, or the population price of the textbooks, of 140 plus or minus 11.5. Or mu goes from 133.5 to 156.5. Still, how is this relates to what we did before, the hypothesis test? Now, if you recall, what we had is that we did not reject the claimed value of $150. Now, if you look at the estimation range here, or the confidence interval, it is from 133.5 to 156.5. And what does that mean? It means that the claimed value of 150 falls between these two values of the confidence interval. And that is why we could not reject the null hypothesis of mu equal 150, because it falls within the estimated value of the population mean. This is a very, very important point to illustrate the relationship between the confidence interval and the estimation process and the hypothesis test. As a result, we made the right decision, since mu exhibits an interval estimate, or a possible range, which contains the claimed value of $150. A company is interested in investigating the medical cost of its employees. Based on consulting a medical cost research organization, the mean medical cost was claimed to be $21,000 annually. Now, in order to verify this claim, the company took random samples of 30 people from each division and determined the medical cost of the employee. This is exactly what happened in practice. They take many samples, each of the same sample size, and using these samples, the company constructed a sampling distribution, a histogram of the sample means. This histogram of the sample means or the sampling distribution had a mean value of $20,000. Now, from past record, the variance of medical cost is known to be 100 million. And the question is, can we verify the claim of $21,000 annually of medical cost at 1% risk or 1% type 1 error? Now, following the previous steps, we have all what we need. We have X bar equal $20,000. Sigma, recall that what we given you is the variance, not the standard deviation. And the variance was 100 million. But we need the standard deviation in order to perform the hypothesis test. And the standard deviation, as you recall, is the square root of the variance. So we need the square root of the 100 million, which is 10,000. Now, the sample size is known as 30. The claimed value is 21,000. The type 1 error is 1%. And this is the format of the hypothesis test. So we need to follow the previous steps one by one. Here is the first step. We establish the test of hypothesis format. Null hypothesis mu equal 21,000. Alternative hypothesis mu not equal 21,000. The sample statistic that we need here is the average X bar, $20,000. And we have the sample size 30. The type 1 error, we know it is 0.01 or 99% confidence, if you recall, which correspond to a z-value, a critical z-value of 2.58. Then we calculate the Z statistic, X bar minus the claimed value divided by the standard error, 20,000 minus the claimed value of 21,000 divided by 10,000 divided by the square root of 30. That give us a Z statistic of minus 0.548. And we sketch the normal distribution to be able to make our decision of whether we reject or not to reject the null hypothesis. And as you can see here, the critical values are the boundaries of the no rejection region, and the rejection regions are the outside regions. And when we say rejection regions, we are talking about 0.5% here and 0.5% here. Now notice the Z statistic happened to fall within the do not reject region. It is minus 0.548, so it had to be here. Keep in mind that the center of the standard normal distribution is 0. So here is 0. The right to that is positive, the left to that is negative. You don't want to forget this basic information. So as a result, we cannot reject the null hypothesis, meaning we have to accept the fact that the population mean could be $21,000 annually of medical cost. Now one more time, we're going to link or bridge between hypothesis test and the estimation. We have all the information we need. We can estimate the population mean as mu equal X bar plus or minus Z times the standard error. And what we have here is an estimation value or interval value. The standard error is 1,825.74. If we multiply it by 2.58, that will give us a margin of error of 4,710, or a percent margin of error of 47110 divided by the 20,000, the point estimate, that gives us 23.55%. So what does that mean? It means that we have an estimation of mu from 15,289 to 24,710. And if you recall, what we did as far as the hypothesis test is we did not reject that mu is equal to 21,000. But notice that the interval estimate here, goes from 15,289 to 24,710, which means the claimed value fall between these two values. And this is what we see here. Here is the sketch of the normal distribution, and we can conclude that we made the right decision since mu exhibits a value or exhibit an interval estimate or a possible range which contains the $20,000 or $21,000 in between. So that is how we link the hypothesis test with the estimation process. Here is another example. The mayor of a large city claims that the average net worth of families living in this city is at least $300,000. Now I want you to pay attention to the term at least. Meaning this mayor claims that the average net worth of families can be actually greater than the $300,000. Now, a random sample of 25 families selected from this city produced a mean net worth of $288,000. Now, assume that the net worth of all families in this city have a normal distribution with a population standard deviation of 80,000. Now, using the 2.5% significance level or the 2.5% type 1 error, can you conclude that the mayor's claim is false? Let's see. What we have here, step 1, is we establish the hypothesis test format. Now, the mayor is saying that the average net worth of families living in this city is at least 300,000. So obviously what we are trying to test here is that mu is greater than or equal the $300,000 that the mayor claimed. And that would be our null hypothesis, that we assume it is true until we prove otherwise. Now obviously the alternative to this is that no, some families may have an average, or the population average may actually be less than $300,000. So we have the null hypothesis and we have the alternative hypothesis. Now the second step is that we know the population standard deviation sigma is known. We also know that the sample size is small, but the population distribution is normal. Consequently, we will use the normal distribution to perform the test, or we will use the Z statistic. So we know that at alpha 0.025, if you recall alpha 0.025, we are saying here alpha. So that is the entire value of alpha. This is a one-sided test. So we put in the whole type 1 error or the whole risk in one side, basically the left side or the left tail of the normal distribution. So at alpha 0.025, we know the Z value is 1.96. You do not want to make this mistake here. This is not a two-sided 95%. It is a one-sided, and it is not a 95%. It's actually 97.5% confidence, meaning 2.5% would be to the left tail. This is what I meant by saying that we put the entire risk in the left side of the distribution. So now we need to calculate the Z statistic. And we already know that the critical value is minus 1.96. So the standard error, which is sigma divided by the square root of the sample size, sigma is 80,000 divided by the sample size square root, which is 25. So now we have a standard error of 16,000. That means Z being x bar minus the claimed value of 300,000 divided by the standard error will give us minus 0.75. Now, the minus 0.75 is right here. Now keep in mind that if we are in the shaded region here, this is the rejection region. while the area to the right is the no rejection region. So since the Z statistic is in the no rejection region, then we simply cannot reject the claim of this mayor that the average net worth of families in this town or in this city is at least $300,000. This is a very rich, small city, as you can see. Now we move to the second condition, which is what if the standard deviation of the population is unknown? And again, in parallel with what we did in estimation, we have three situations under this condition. The first one is if we have a small size sample, n less than 30, but we're willing to assume that the variable of the population is normally distributed. The second situation, if the sample size is large, 30 or more, and we said that since we do not know the standard deviation of the population, we will have to refer to the T statistic or the T distribution to estimate mu. In this case, since we are talking about hypothesis test, we will refer to what we call the T statistic. Now, the T statistic is simply equal to the average of the sample minus the claimed value mu0 divided by the standard error. So the format is very similar to the Z statistic format. The only difference is we no longer know the population standard deviation, and we have to rely on the standard deviation of the sample. This table should also look familiar. It gives you the hypothesis format, the null and the alternative. It gives you the T statistic. It gives you the critical statistic, which is the T statistic from the T table, which is determined by the degree of freedom and the type 1 error. And it gives you the criteria for rejection, which is really the T statistic falling within the rejection region of the T distribution. Let's take an example. Determine the T statistic, the critical T value, and make appropriate decision for the hypothesis test for the following cases. What we have here, X bar is 80, that's the average or the mean of the sample. The standard deviation of the sample is 5, the sample size is 10, the claimed value is 82, and we have a type 1 error of 0.05. And here is the format of the hypothesis test. Mu equal 82 or mu not equal 82. So we calculate the T statistics, and the reason we use the T statistics here again is we do not know the standard deviation of population, only the standard deviation of the sample. So the T statistic here is X bar minus the claimed value divided by the standard error, or 80, the X bar value, minus 82, the claimed value, divided by 5 divided by the square root of 10, so we have a minus 1.265. Now if we go to the T table, we will find that a degree of freedom of 9 and alpha 0.05, that the T value will be equal 2.262 or minus 2.262. That is the two-sided critical values of T. So what does that mean? This simply means we have a critical T value of 2.262 minus or plus, as you can see, while the value of the T statistics is right here. It's a minus 1.26. So as a result, the T statistic fall within the do not rejection region. So we cannot reject the null hypothesis. If we use the area or the p-value, we can also see here that the p-value corresponding to the T statistic, which is, if we multiply it by 2, it will be 0.2377. This area is greater than the 0.05, which is the type 1 error value. And that gives us another reason why we should not reject the null hypothesis of mu equal 82. Here is another example, which will also allow us to bridge between the hypothesis test and the estimation concepts. A claim was made of strict grading in a new math course. Normally, colleges are concerned about either a grade inflation, where the grades of a certain course is typically higher than the average, or the other extreme, which is strict grading. And since this is a new course, the college really needs to see how this course is doing with regard to grading. Now, the concern here is that since this is a new course, the grade average of this course is low. So the claim indicates that students in this course make a point average of only 2.3. Now, to test this claim, the math department took a sample of only 10 students and listed the grades, as you can see here. These are the grade averages. Now, we need to assist the department in testing the claim at a type 1 error of 1%. Now, this is a small sample. We do not know the population standard deviation, since this is a new math course anyway. So we're going to have to rely on the sample statistics. Now, we have to establish the claim first. The claim is that the average grade of this course is typically 2.3. So that should be the basis for our null hypothesis. The alternative hypothesis is that mu is not equal 2.3. So now we can calculate the mean of the sample, which happened to be 2.21, the standard deviation of the sample, which happened to be 0.1449, and we know the sample size. That allows us to find the t-value, the critical t-value, based on the degree of freedom, which will be 9 since the sample size is 10. It will also allow us to calculate the T statistic. So here is the T statistic first. X bar minus the claimed value divided by the standard error. So given these values, we have a T statistic of minus 1.97. We need to compare this with the critical T value at a degree of freedom n minus 1 or 9, and at alpha equal 0.005 or alpha over 2, 0.005, since alpha is 0.01. We're talking here about a 99% confidence. So if we go to the T table, and at a degree of freedom of 9, and the alpha alpha over 2, 0.005, we will find that the t-value is 3.25. So now we have the critical value of t at a degree of freedom 9, sample size 10 minus 1, and at a type 1 error of 0.01, since it is divided by 2, it will be 0.005. So here is our t-value, critical t-value, and here is our calculated t-value. So we simply have to compare between these two to see whether the T statistic fall within the rejection region or the non-rejection region. And here we go. We sketch the T distribution. Here is our critical value from minus 3.25 to plus 3.25, and as you can imagine, the T statistics is right here. It's minus 1.97. Keep in mind one more time that the center of this distribution is 0. So that's why the minus 1.97 would be located here. And since it is located in the do not reject region, then we simply do not reject the null hypothesis, and we can easily tell the math department that yes, the average grade point of this new math course is 2.3, and this is maybe a strict grade average. Again, we can verify this using estimation. Here is our X bar, here is the standard deviation, this is the sample size, and here is the claimed value of 2.3. Now, if you recall, when the standard deviation population is unknown, we estimate mu using the T critical value, and as you can see here, mu is equal the point estimate X bar plus or minus T times the standard error, and that gives us 2.21 plus or minus 0.149, which is the margin of error. Now keep in mind this is the standard error, and the product of T times the standard error will give us the margin of error. So 0.149 is the margin of error. If we need the percent margin of error, we will have to divide the margin of error by the point estimate times 100. That will give us the percent margin of error, which is 6.74. But the point to be made here is that the interval estimate at 99% came out to be 2.21 plus or minus 0.149. And what does that mean? It means it ranges from 2.061 to 2.359. Now keep in mind that the claimed value was 2.3. Now you notice here that the 2.3 definitely fall within this range. So as a result, when we decided not to reject the null hypothesis that mu is equal to 2.3, we were absolutely right, because that 2.3 fall within the estimated confidence interval of the population mean. Let's take another example here. A manufacturer of voted boards used for making office desks has started to use a new surface finish treatment. So we have a supplier of finished treatment of wood, and we know how important it is to have a wooded surface that can resist oil or any spills, drinks or whatever. And this treatment here, according to the provider or the maker of the chemical, is claimed to have an absorption rate of 1.2%. Okay, so the provider of the surface treatment claimed that on average the absorption rate is 1.2%. Now the maker of the tables or the wooded board may want to test that. So in this case we took 26 boards and we tested them to see the absorption rate using the new treatment that's claimed. So let's look at the data here. What we have here is the board ID 1 to 26, and here are the absorption rate measured by some techniques in which they actually measure the absorption rate of any stain or any type of liquid. It's a real surface tension method, but we are not going to get into that. And what we have here is 26 values of absorption rate that we will use to test the claim by the provider that the average absorption rate is 1.2%. And as you can see here, we have values that are lower than 1.2%, and we have values that are above the 1.2% claimed. So what we do, we have an average value that we calculate from this data. We have a sample size of 26. That's a small sample, and we need to pay attention to that. And if you recall, to find the t-value, we have to determine the degree of freedom, which was the sample size minus 1. So if the sample size is 26, the degree of freedom would be 25. And then we have the standard deviation of 0.32 calculated from this set of data. And here is our format of the hypothesis test. We will follow the mu equal versus the mu not equal. And what we see here is mu equal 1.2, mu not equal 1.2. Then the next step we will do or calculate this T statistic, which is x bar 1.08 calculated from the data, minus 1.2, this is the claimed value, divided by 0.32, this is the standard deviation calculated from the data, divided by the square root of the sample size, which is the sample size or the number of observations we have to deal with. And that gives us a T statistics of minus 1.91, as you can see. So what's the next step? Well, the next step is based on the type 1 error that we are willing to commit. We need to find the critical t-value. In this case, we're going to use a 1% type 1 error or 99% confidence. And if we go to the t-table, we will find that at degree of freedom of 25 and at value of alpha over 2 of 0.005, which is really 0.5%. Remember, we divide the 1% into 2 halves. The t-value will be 2.787. And if we sketch the normal distribution, we will see that this critical value here is 2.78, which is right here. This is where the critical value is. This is the threshold for reject or not reject the hypothesis. While we have a T statistics of minus 1.91. Well, if we sketch that where it's located in comparison with the critical value, we will see that the 191 will be inside the area of confidence. As you can see here, T0 is minus 1.91, which is inside this critical zone, since this value here, as we know, is 2.787. So we have no choice but to fail to reject or not reject the hypothesis test. Meaning we're going to accept the provider claim that the value of absorption rate is actually 1.2. We have no reason to reject that. Now we can also confirm what we just did by recalling what we did in estimation. If you recall, in this case, to establish a confidence interval, we have used this formula here. And as we can see here, by establishing a confidence interval, we see that mu, or the absorption rate, will range from 0.906 to 1.26. Now remember, the claimed value was 1.2. So when we do the confidence interval, we're finding that mu is indeed can be this value of 1.2, because the 1.2 fall within the range from 0.906 to 1.26. This is the reason why we fail to reject the null hypothesis, because by the alternative way of doing it, which is estimation, we're finding that the absorption rate by the data we collected can indeed be within that range. So our conclusion is to fail or not reject that mu is equal 1.2. Suppose in the same example that the manufacturer of voided boards is more concerned about the absorption rate being too high. Okay? After all, we want the surface of the voided board not to absorb any spills or any water. Okay? So now we are looking at a smaller the better category, which means we have to reformat our hypothesis test. So we are really concerned about the value of absorption rate exceeding some threshold of 1.2. So accordingly, as you can see here, we're changing our format of hypothesis test. Here we are using mu greater than or equal mu 0 versus mu less than mu 0. So this is a one-sided test, where mu is greater than 1.2 is the null hypothesis, and mu less than 1.2 is the alternative hypothesis. So in this case, we will do the same analysis. We will calculate T0, okay? Because it should be the same. We have X bar the same. We have the claimed values the same, standard deviation of the sample and the sample size. But the critical T value will have to be different. At 99% confidence or at 1% type 1 error, this time we are looking at a degree of freedom still at 25, but at a critical value of 0.01, because we are locating the entire type 1 error in one site. Here it is, the 0.01 or the 1%. And if we go to the T table, we will find that at degree of freedom of 25 and type 1 error of 0.01, the T value this time is 2.485. Now we have, here is the critical value from the table, 2.485. And here is our T statistics. And as you can see here, the T statistics is still in the do not reject region. What does that mean? It means we fail to reject the hypothesis that mu is greater than 1.2. In other words, mu can indeed be greater than 1.2. Now note that when we did the estimation a minute ago, the range was from 0.906 to 1.26. So when we say that we fail to reject that mu is greater than 1.2, we are correct, because the value of mu can be all the way up to 1.26. That's why both approaches, the confidence interval and the test of hypothesis, have to be used simultaneously in order to make sure that our decision is appropriate.